Rahim. Last time we introduced the wavefront method. Today we are going to take up a numerical problem and see if we can solve it using the wavefront method. Now this sort of a structure is given, three elements, and let's number the nodes like this, and the stiffnesses for each are easily calculated like this. In our case, young borders 1, 2, 3 is the same, it's steel, so it doesn't matter. Only the areas and the lengths are also the same, so basically only the areas make a difference. This is 40,000 Newton per millimeter. That is, K1 will be, in our case, K1 will be 40,000 minus 40,000 minus 40,000 and 40,000. Now K2, A2, E2, L2, E and L happen to be the same. 10 is by 300. This is 60,000 Newton per millimeter. That is, K2 will be 60,000 minus 60,000 minus 60,000 and then 60,000. Similarly, K3, A3, E3 over L3. This area here is now 10 into 200, 10 is for 3 over 100. This is 20,000 Newton per millimeter. That is K3 20,000 minus 20,000 minus 20,000 and 20,000. So now we have this situation where we have all the values. Now we take up element number 1. We always start with element 1. Element 1 is very simple. 40,000 minus 40,000 minus 40,000 40,000 U1 U2 is equal to minus 1,000, minus because it is opposite to the positive x direction. Here you have 0. So now let's call this just to locate this is 1, 2, degree of freedom 1, 2. Now this is the last occurrence of degree of freedom 1, that is U1. It's not going to be repeated again. In element 2 you have 2 and 3, so this is the last occurrence, so we can eliminate it now. But again, there is a problem here. It's all very well to write this equation as 40,000 U1 plus minus 40,000 U2 is equal to minus 1,000, and then we can write U1 in terms of U2. We can do that, but the issue is, by row operation we cannot make this minus 40,000 0, and this minus 40,000 needs to be 0 for us to be able to eliminate this U1, because this gets multiplied with U1, this 40,000. If you use row operation, then this becomes 0, but this everything vanishes. So we would like to eliminate U1 here, but we cannot. So let's move on. Add element number 2. Now element number 2, again connectivity. If you recall the connectivity, we don't actually have to make the connectivity table, but it's very simple. But just for demonstration purposes, for element 1, node 1 and 2, For element 2, node 2 and 3. For element 3, node 3 and node 4. This is your connectivity table. These are nodes. This is I node and this is J node. These are elements. Now, element 2 obviously will be added in this way, because this is 1, 2, and for element 2 now you have 2 and 3 degrees of freedom. So 1, 2 and 3. So 40,000 minus 40,000 minus 40,000. Here you have 40,000, but this one, but element 2 also occupies this. So you have 60,000 minus 60,000. This is simple connectivity, and there is no difference in this step whether it's the ordinary approach or the wavefront approach. So this is just simple repetition of what you have been doing. Now we can eliminate degree of freedom 1. How? Because now we are in the happy position of being able to make this 0 without making all this disappear. How will we do that? Very simple. Add R1 to R2. We want to make this 0. And why we want to make this 0? Because ultimately we want to eliminate this U1, this row and this column. This row, if we can write the equation of U1 and store it somewhere, it's no problem, this elimination like this. But with this also goes, but this is being multiplied with U1, so some information will be lost. We don't want to do that. So if we do that, this is the row operation. Write first equation as it is, and recall that row operation has to be carried out on all the rows, not just all the entries, not just the entry that you require. So this plus this becomes 0, but you have to repeat the same thing across the board. So this becomes 60,000. This is unchanged because this is 0. This one you don't need, you have no need, because this is already 0. If this was a number here, some non-zero number here, then this would also be multiplied with U1, so you would have needed to make this 0 also, but luckily this is already 0 for us, so this remains unchanged. And the important thing is you have to do the same operation on force vectors also. So adding R1 to R2 means this also becomes 1000 and this stays 0. Now you are in a happy position to eliminate this and this, but not before you write the equation for U1, that is 40,000 U1 minus 40,000 U2 is equal to minus 1000, or in other words U1 is equal to 40,000 U2 minus 1000 over 40,000. This is the equation that you need to store. Having done this, and because these are all zeros, so you can just eliminate these and recall that this is 1 2 3 and this is 1 2 3. So if that is the situation, then your this matrix actually becomes this only. Two by two. So you have this 2 by 2, then it became 3 by 3, again 2 by 2. So it went up. You started from here 2 by 2, then 3 by 3, but then you come down again 2 by 2 in this step, because this one has been eliminated and written for later use. Now let's move on. And recall that this is second degree of freedom, third, second, third. Let me, because we are going to do an operation on this one, let me reproduce it as it is. 60,000 minus 60,000 minus 60,000 and 60,000. U2 U3 is equal to minus 1,000 and 0, and this is 2 3 2 3 location. Again we have the same problem. In fact, at this point, because we have reached element 2, the next one is element 3, so already degree of freedom 2 is already irrelevant now. But again we have the same problem as we had here. We would like to eliminate this u2 here, but we cannot, because there's no way you can make this 0 without making everything disappear. Everything will become 0. So we have to bear with this situation for a while and add element 3 now. Element 3 will be added, obviously. It will be added 2 3 4 in the 3 4 places. Minus 60,000 minus 60,000. Here you have 60,000 plus element 3 values for element 3. This 20,000, this comes at this 3 4 location. So simply plus 20,000 minus 20,000 minus 20,000, 20,000, you have zeros here, u2 u3, you have u4 here, minus 1,000, 0 0, there is no force here. Now we can eliminate. Now at this stage we can eliminate degree of freedom 2, because simply we can just add r1 to r2 and this will become 0. If this becomes 0, then we can just eliminate this. So first one remains unchanged. You are adding the first one to the second one, so there is no difference to the first one. So here becomes 0. Here you have 20,000. Here you have minus 20,000. Here it is again unchanged. Same reason, it is 0 here already, so you don't need any, because you need a 0 here for this to go, but it's already 0, so nothing that you need to do. And when you add row 1 to row 2, you have to do the same thing on the force vector also. Now this is where we can just remove this and this, but not before we write the equation for u2, because we are going to use it in back substitution. Remember, 60,000 u2 minus 60,000 u3 is equal to minus 1,000. u2 is equal to 60,000 u3 minus 1,000 over 60,000. Again you write it to, when you're doing it on a computer, you are writing it to the hard disk. Here we have already written it. Now at this stage, 2 3 4 2 3 4. Now these are all zeros, these zeros, no problem, gone, and this one also gone because you have written it here. So you have 20,000 minus 20,000 minus 20,000, 20,000 u3 u4 is equal to minus 1,000, 0. Now recall that here we had reached from 2 by 2 to 3 by 3, then 2 by 2 again. Here this is 2 by 2 again, then we went to 3 by 3 again. this, but again we came down to 2 by 2 here. So actually if you take this system and do it by the ordinary approach, 1 2 3 4, your system will be 4 by 4. Yeah, 1 2 3 4 6. We never reached 4 by 4, we are here, so we went up to 3 by 3, but this is a smaller system, so the difference is not very large, but for bigger systems you will have significant saving of your computational power. Now power requirement. Now this is the situation where you have 2 by 2 matrix and you have reached the point where this boundary condition is reached. Now u4 is equal to 0. Now u4 is equal to 0 means this is a specified boundary condition. And we deal with this sort of a system, this sort of a boundary condition, in slightly different way than we do it with these unspecified displacements. There we obviously we eliminate rows and columns. Here also we eliminate rows and columns, but here we do it in a slightly different method, and that is row operations are not needed. What we do is simply for u4 is equal to 0, we will eliminate this one, this line, this column, this row. The only issue is that this minus 20,000 is being applied with u4. So when we eliminate this, if this u4 was anything other than zero boundary condition, this is zero boundary condition, but if it was some number, then we could not have simply eliminated it like this. We would have multiplied this number with this, whatever this number was, and then taken it to the other side. Recall our lecture. And then once this is 0, then we can simply replace it like this. But here, because the boundary condition is zero boundary condition, so we don't need to actually multiply this with anything, it's 0. So gone on the other side with sign change is still 0, so no need to do that. So our problem is solved here, we can just remove this. But in case we need our reaction force calculation, then we need to write this equation. We write again minus 20,000 u3 plus 20,000. So here the writing of this equation is not for the sake of calculation of boundary, this value of u4 is already known, but in case we need to calculate R4, reaction force 4. Now this is the equation. Now this u4 becomes 0. How? When a reaction force is added. This wall, how does this wall ensure that u4 is 0? By applying a force here. Without force it cannot maintain this 0 boundary condition or whatever boundary condition. Force is required to keep this from moving. So whenever boundary condition is applied, there is a reaction force also. Now this is not an applied force, but it is a reactive force. So if later on we want to find out the value of R4, then it is simply minus 20,000 into u3, because u4 is already 0. So we just write it again, write it down. And if we have written it like this, and considering that this boundary condition is 0 boundary condition, so it doesn't matter if this is not 0. So we can just, now in a situation we can just do it like this. And when we do it like this, then what remains is simply 20,000 u3 is equal to minus 1,000. Now this is actually 1 by 1 system, or in other words, just 1 degree of freedom left in the system, which means you now are at 1 into 1 stage. This is the 0 line. Here you cannot simplify it further anymore, so, and you don't need to. basically this is nothing but 20,000 u3 is equal to minus 1,000, and if you calculated u3, it turns out to be minus 0.05, and it would be millimeters because we have been keeping everything in Newton and millimeters and Newton per square millimeters. When we write this E as 210 is per 3, then this is in MPa or Newton per square millimeter. So everything is in, forces are in newtons, distances are in millimeters, areas millimeter square, so, and this is also millimeter square. So if we maintain this sort of a system, then we can be sure that our displacements are in millimeters. u3 turns out to be minus 0.05, and then if you back substitute, you have this u2 value here and u1 value here. This is what we meant by back substitution. u4 already known, u3 calculated, and then you just plug in the values. We use this expression, u2 is equal to 60,000 u3, which and minus 1,000 over 60,000, that is 60,000 u3 is minus 0.05 minus 1,000 over 60,000, and u2 turns out to be minus 0.067 millimeter. Now if this is solved, let's bring in the equation for u1. Now it's simply a matter of plugging in the values. 40,000 u2 minus 1,000 over 40,000. 40,000 into minus 0.067 minus 1,000 over 40,000, which turns out to be this one. Now obviously values are all in negative. It makes sense, this force is in the negative x direction, so the values must be in negative. So if we summarize this, u1, u2, u3, u4 is minus 0.092, minus 0.067, minus 0.05 and 0. This is the specified quantity. These are all in millimeters. Now the rest is simply post processing. Let's do it. This is not, now wavefront method is over. Now post processing is simply calculation of strains and stresses. Epsilon 1 will be u2 minus u1 over L. u2 minus u1 over L. Similarly, epsilon 2 u3 minus u2 over L. Similarly, u4 epsilon 3 u4 minus u3 over L. So just plug in the values again. Minus 0.067 minus plus, because this you're talking about 0.092 over 100. So epsilon 1 is 2.5 into 10 raised to the power minus 4. Epsilon 2 u3 minus u2 over L, that is minus 0.05 minus plus 0.067 over 100. So epsilon 2 is, turns out to be 1.7. And notice that although all these displacements were negative, but strains are obviously tensile. In this system there's no compression, so it doesn't matter. This displacement actually, the coordinate axes, they don't cause a change in compression or tension. That is a physical thing. So and which makes sense, it shouldn't. u4 minus u3 over L. Now u4 was 0, minus sign plus 0.05 over 100, and epsilon 3 is basically 5 into 10 raised to power minus 4. These are dimensionless quantities. Now sigma 1 is equal to Young modulus and epsilon 1. You just multiply this with these with epsilon 1 is equal E1 is equal to E2 is equal to E3, 200 into 10 raised to power 3 MPa. Recall this. So if you multiply this with this, you get 50 MPa. Epsilon 2 sigma 2 E2 into epsilon 2, and this turns out to be 34 MPa. Makes sense. Forces basically this is 1000 force here divided by 20. This the larger, you should expect the largest stress here, as you will see, and sigma 3 is equal to, this turns out to be 100 MPa, and this is, it makes sense, the smallest area should have the highest stress. Now here although we did not calculate it, but and we didn't need to, for stresses you don't need to calculate reaction forces, but in case you needed it, for some questions it is required, although usually it isn't. This is the expression for reaction force. R4 is equal to minus 20,000. So if in a certain question we need to calculate reaction force, then it can easily be done. This is not needed here, but reaction force calculation, R4 again from what we had written, minus 20,000 into U3, minus 20,000, U3 value is minus 0.05, which is minus 1000 Newton. Now again, this makes great sense. R4 is plus 1000. It doesn't make sense. Minus doesn't make sense. Plus makes sense. Why plus makes sense? 1000 Newton in the plus direction. That is, if this is the applied force, then for the displacement here to be 0, a force of 1000 must be applied in this direction, which makes sense because minus 1000 plus 1000, the whole system is in equilibrium. So this makes great sense, and this also confirms that the equations, the algorithm that we discussed last time, that works. And although we don't do it like this, but now this example shows you how to deal with the elimination. Whenever a certain degree of freedom is not expected to be used again, you eliminate it. But we also discussed something about the boundary conditions, specified boundary conditions, when they occur for the last time. If that is the case, this example is not suited to demonstrate that, because in this example your boundary conditions, specified boundary conditions, comes at the very end, and at the very end this is how you tackle your boundary conditions in the ordinary approach too. So I wasn't able to demonstrate the boundary condition if it occurs first. Now let's turn this problem around. This is the same problem, exactly the same problem, but now I've turned it around so that for this sort of numbering, you see that if we start with element 1, then at the first instance this boundary condition will be applied, because the moment we make the equation for the first element, after that this node 1 becomes irrelevant, so we can eliminate it. So in this case, by the same calculations, the k values will be k1, k2 60,000 and k3 40,000. Now these are reversed. K1 and k3 are reversed because recall that in this case 1 was 20 millimeter diameter here, and 3 was 10 here. Number 1 is 10, so these are reversed, but apart from that there is no change. But as far as the problem is concerned, both these problems are identical in that the stresses in 2 must be equal to each other. The stress in 1 will be equal to stress in 3 here, and stress in 1 here will be equal to stress in 3 here. Otherwise it's identical, mirror image you can say. So these are the numbers. Now we start with element 1 as usual. 20,000 minus 20,000 minus 20,000 and then 20,000. U1 U2 0 0. Now this is 1 2 1 2. Now U1 is equal to 0. We know that U1 is equal to 0. Straight away we are facing this specified boundary condition. Now that means that we should look to eliminate this column and this row and this column. And furthermore, because this would have caused problems if U1 was not 0, because this would have been then multiplied with U1, and in that case we would have taken the product of this with this number, whatever this number was, non-zero number, and then taken to the other side and add it here, and then this became 0, and then we would have eliminated. But now because this is being multiplied with 0, so it doesn't matter, so we can just eliminate it. But before eliminating, obviously we need to write this equation, this in this case not for boundary condition, not for degree of freedom, but for reaction force if it is needed. So we'll eliminate this, but before eliminating we'll write 20,000 U1 minus 20,000 U2 is equal to 0. This is the equation, and this U1 becomes 0 precisely because R1 is added. There's a reaction force added here which makes sure that this U1 is 0. So if that is the case, then R1 value is minus 20,000 U2. Let's write it down like this. And now because of this written, we can get this, because this we have written, so no need to worry about losing any information here. And because this is being multiplied with 0 boundary condition, so there's no problem here also. So here we are left with 20,000 U2 is equal to 0, and this is just 1 into 1. So if we make a similar graph like we did last time, in ordinary approach we would expect something like n into n size. Here we started with 0, and then we reached 2 into 2, and then it suddenly becomes 1 into 1. Now we add element 2. The rest is very simple, very similar to what we did last time. Element 2, again the connectivity is, we don't even need a connectivity table here. Element 1 1 2, element 2 2 3, element 3 3 4. So when we add element number 2, then we are talking about 2 3. So 1 2 3 1 2 3. This is even 1 is not needed. 1 is gone. So basically we are talking about 2 3 2 3. 20,000 already there, and here you have this node 2, so plus 60,000 minus 60,000 minus 60,000, and then you have 60,000. u2 u3 is equal to 0. Still no force either at 2 or 3, so we have this. Now we can eliminate u2. Again, u2 is not irrelevant because the next element is element 3, and element 3 doesn't have u2, so we can eliminate degree of freedom 2. Degree of freedom 2 will be eliminated. Now this elimination will be exactly like the elimination we dealt with in the problem that we faced earlier, which was mirror image of this, because now this degree of freedom 2 is not a specified one, so some sort of row operation will be needed. So first just write it like 80,000, just rewriting it. This is not a new equation. 2 3 2 3. We want to eliminate this u2. We will write it down here, so we can do that, but this is problematic. This has to be 0 because this multiplies with u2, and unless this is 0 we cannot just remove it. So what we do is, somehow with row operation we want to make this 0. That is very simple. If we add actually 6 over 8, 60,000 over 80,000, that is the factor. Add 6 over 8 r1 to r2, then it's very easy to see that this first line obviously doesn't matter, it's the same. Six multiplied by r1 over 8 is 60,000. Added to 60,000, this becomes 0. Similar operation has to be done on the other two entries also. This becomes 15,000. This is 0 because this is 0, so it doesn't matter. Both of these are 0. So again, this became 1 by 1. Then you added another element. Again, it became 2 by 2 here. But now you are in a position to, because this is 0, if only you can write it 80,000 u2 minus 60,000 u3 is equal to 0, and then if you can write u2 is equal to 60,000 u3 over 80,000, you can simplify this. 6 over 8 u2 is basically 3 over 4, 0.75 u3. You just write it down. So now if you eliminate this, because this information is already here, if you eliminate this, because this is 0, doesn't matter, 0 multiplies with anything, so again you are left with 15,000 u3 is equal to 0, and this is again 3 2 3 2 3, so this is 3 3. Actually these are just a number, okay? So again you are back to 1 into 1. So this n into n, this is in this case 4 into 4. So you will not even reach, in this case you will not even reach half of it, you will reach just half of it precisely. In the last case you reached 3 by 3. There was a slight less of a saving here, but the point is that for larger systems the saving will be very large. Even for this system, the saving in the working memory requirement is 50%, even for this smaller system. So you have this sort of situation here. Now obviously the next step is to move towards the last element, and nodes are 3 and 4. So we just add 40,000 and let us do that now. We already have 15,000 here, and this is 3 4 3 4 15,000 plus this 15. This is already there for 3 3 place. Add 40,000 minus 40,000, minus 40,000, 40,000, and you have u3, u4, and for the first time here you have a force, because the force has been 0 throughout. Here you have 1000 Newton, and this one is positive because this is positive x direction. Now obviously this is the last element, so both u3 and u4 are not going to be repeated, but u4 is the last one. We have to retain this. We'll calculate this one, so this you can eliminate. And for this it's simple matter of first of all writing this as 55,000 minus 40,000 minus 40,000 and 40,000, u3, u4, and eliminating degree of freedom 3 now, which is a matter of simple, actually 40 over 55, 40,000 over 55,000. This will give you the factor, that is 40 over 55. It can also be written as 8 over 11, 8 over 11 r1 to r2. This is 3, 4, which means that first one remains as it is. We are not going to change it any. This one becomes 0 because this multiplied with r1 precisely is 40,000. Here it is minus, so when you add them this becomes 0. Same operation if done here, you will get something like 10909.1, and this one, because this is 0, so it doesn't matter, this remains the same. And now you can just eliminate it because this is 0. You have to make this 0 before eliminating, but before eliminating it you have to write this equation: 55,000 u3 minus 40,000 u4 is equal to 0, and u3 is equal to 40,000 over 55,000 u4, which is 0.727 u4. Write it down like this. Now this is 0, this has been written, so you can just easily eliminate this. So what remains is 10909.1 u4 is equal to 1000, 3, 4, 3, 4. This is 4. But this is just a number. 10909.1 u4 is equal to 1000. This is not a matrix anymore, which means that u4 is equal to 1000 over this, and that is 0.092 millimeter. Now the rest is simple. Back substitute u3 0.727 into 0.092. That is u3 is equal to 0.067 millimeter. Now u2 is 0.75 into u3. u2 is equal to 0.75 into 0.067, which is 0.05 millimeters. Now if you were to calculate the reaction force, you don't need to, but if you were to calculate it, we have it right here. Reaction force 1 is equal to minus 20,000 u2, that is minus 20,000, and u2 is 0.05, that is minus 1000 newtons. Again, makes complete sense. This is 1000 plus, so there has to be 1000 in the negative direction for this system to be in equilibrium, and that is the force in this direction that makes sure that u1 is equal to 0. That is a reaction force. So you can you have verified this also. Now your system is, in this case, u1, u2, u3, u4. In this case Your u1 is 0 because boundary condition, it is 0.05, u3 is 0.067. all the numbers are the same as last time, only in positive. They are all positive because the force is in the positive direction, so displacements can only be positive. But it's very obvious that if you calculate the strains and stresses, you'll get identical results. Please verify that. And by this second problem, it's the same problem, but essentially it's a mirror image of the same problem. This particular version actually gives you the illustration of how to apply the specified boundary condition. The last one didn't, but after that the steps are the same. So here you can see how much saving you have achieved, even in a system as small as this one. You can imagine that if a system is 10,000 by 10,000 or 100,000 by 100,000, what sort of saving can be expected in the working memory. Thank you.